It is now my absolute honor and privilege to introduce our very first presenter of the day, John Nielsen Gammon. John is Texas's state climatologist and a Regents Professor of Atmospheric Sciences at Texas A&M. We couldn't possibly start a day of conversation about being rooted in resilience without first grounding ourselves in the science of climate and the future of the Hill Country. So please join me in welcoming John Nielsen Gammon to the stage. Thank you, John. All right. You got this? Thank you. Here we go. We've got your slides.
Thank you very much. The Hill Country is a place that's especially sensitive and reliant upon the weather and climate. It shapes the landscape in turn feeds back upon it. So I want to do, and as we've seen with events over the past several months, we really have to be conscious of what the weather and climate can do on this landscape. So I'm going to talk about the basic climate that we have to deal with here. It has special challenges beyond just the normal weather we get in Texas. And I'll be showing slides and images from a variety of sources, including a book that's in press that should be coming out in a few months on climate change impacts in Texas, integrated analysis and adaptation. So for starters, temperature in Texas is basically in the wintertime increases from north to south. Our cold air comes from the north. It's channeled by the Rocky Mountains. So we have basically a direct line from the Arctic to the Hill Country with nothing but barbed wire to stop it. And that usually is not very effective. The temperatures, you can see the minimum temperatures in the wintertime are flirting around freezing, so we can get hard freezes occasionally. Record temperatures are actually below 0 Fahrenheit on occasion. Summertime, of course, is a different story. There's almost no escaping the heat in Texas, although the Hill Country, being a bit elevated above the surroundings, is an oasis in that regard, both in terms of the temperatures and the shade. So if you're not going to be heading all the way out to the Davis Mountains or something, this is a good place to be during the summer. Rainfall in Texas typically varies from west to east. El Paso gets about 1/10 the rainfall that Beaumont does. Seasonally, the wintertime is less rain than the summer, but there are actually peaks in the late spring and early fall. But if we zoom in on the Hill Country, it's a bit different because there's a large variation from north to south here. And the basic reason for that is the hills of the Hill Country. The Balcones Escarpment is the first obstacle that the moist air feels as it's moving northward from the Gulf of Mexico into the state of Texas. And as a result, air is lifted up. That can produce clouds, can produce rainfall, and that sort of wrings out some of the moisture along the southern part of the Hill Country. So as you go farther north, there's less water in the atmosphere to rain out. So climatologically, you have a variation of about 20 or 30% from north to south, which is a bit unusual for the state of Texas. Usually it's east to west because our moisture is coming from the Gulf of Mexico, and the Gulf of Mexico is only on south of the eastern half of the state. One of the challenges with water in the Hill Country is we're basically on a dividing line between enough water under normal circumstances and perhaps not enough water under normal circumstances. What I'm showing you here is a historical graph of water levels from Lake Waco, which is a characteristic of a place where there's generally enough water. So the dashed line is the amount of water that they're trying to keep in the reservoir to supply water needs. And you can see lots of spikes above that with large inflows, floods occasionally. The dips below that can correspond to the droughts. And the most significant dip recently was in about 2022 and 2023 when the reservoir got close to about 50% of normal, but then a couple of floods took care of that. But you can see normal rainfall is typically going to be enough to keep the water levels close to capacity. An example of a reservoir on the other side of the coin would be O.H. Ivy in the upper Colorado River. And it was constructed in 1992. It managed to fill up within a year, but it hasn't been full for the past 3 decades or so because typical rainfall amounts aren't enough to keep the reservoir replenished in the face of the water demands as well as evaporation. And the occasional large inflow events bring up the water levels, but they typically do not bring it to capacity. And it's conceivable a lake like this may never be at capacity again. But this means that unlike in East Texas, where normal rainfall is great for water supplies, in West Texas, normal rainfall is not adequate, at least for drinking water purposes. You need the occasional heavy rainfall, which unfortunately is more erratic than normal rainfall. And so you can potentially go long periods of time without getting that sort of normal rainfall. Here in the hill country, most places are in between those conditions. And we may actually be seeing a bit of a shift in climate so that the margin between West Texas and East Texas, the margin between normal rainfall being enough or not enough, seems to be gradually creeping eastward. So here's Canyon Lake, built in the late 1960s. It was full by 1969. And essentially for the rest of that century, normal rainfall kept it full. We started having some serious droughts in Texas in the late 1990s, but then especially 2005 and 6, then 2008 and 9, then the 2011 drought, and you see a period of time there where the rainfall, the water levels were occasionally up to normal, but stayed around maybe 70, 80% of normal. But now we've got the most recent drought, which has been going on really since 2022, and up until the large inflows from the Guadalupe River in July, the reservoir was actually at historic low levels, and even that flood was not enough to bring it over more than about 2/3 of normal. So we've got this weird situation where if you look at all of the typical indicators of drought, rainfall, percentage of normal, and so forth, the drought in the hill country, especially the southern part of the hill country, looks relatively mild, but when it comes to runoff and inflows to reservoirs and to some extent recharge of those rapidly recharging aquifers like the Edwards Aquifer, the normal rainfall actually hasn't been adequate, and in terms of water supplies, it really is a serious condition. Here's Lake Travis, similar sort of situation, normally close to normal for most of its history, but we've seen some very big dips recently. They got more rain in the northern part of the hill country than in much of the southern part with this last recent set of events, and so Lake Travis is actually close to normal now, but normal rainfall is probably not going to cut it. We expect to see water levels declining in the absence of flooding. Now, part of what's been going on is a long-term trend in precipitation. On the left is basically looking at the whole history of weather records in Texas past 130 years or so. And the greens are where rainfall has increased by 1 to 2% per decade. And over a century, that adds up quite a bit. In West Texas, rainfall has been relatively constant or has even declined by 1% per decade. And the hill country is on the dividing line of those historic trends. We've looked at more recent trends on the right since 1975. So over the past 50 years, there's been actually a fairly dramatic decline in rainfall in the hill country as well as other parts of southwest Texas. Rates of decline of about 5% per decade. What that looks like if we look at the average rainfall and the average plateau over the past 130 years, there's lots of ups and downs, wet periods, dry periods. The magnitude of the variation is quite substantial. I don't know if you can read the numbers in the back, but the bottom is 5 inches. So basically, you can imagine the bottom of the screen would be 0. And the variations from year to year are more than a factor of 2 in many occasions. That's part of what makes the rainfall in the hill country so challenging, is that it's erratic. And that's true really of all of Texas. You've got strong influences from things like El Nino and La Nina, those sorts of large swings in the climate from year to year that many other parts of the United States don't really have to deal with because they don't have the same impact. Now, it doesn't look like there's much of a trend if you look at it this way, but if you add on a smooth line, you can see that over the past 20 or 30 years or so, there's been a downward dip. And we don't really, as humans, we don't perceive that average conditions have gone down by inches, so we notice the major droughts. So I've tried to highlight here those periods of time where the rainfall has been persistently below typical conditions. And what you see is for 1900 to the mid-1960s, droughts were a very common feature in this part of Texas, especially, of course, the drought of the 1950s, which is the biggest yellow box on this diagram. Since the 1960s, for either because of variations in the climate or luck, the hill country avoided prolonged drought for a long period of time, until basically the drought that began in 2011, which is the next to last yellow box here. And then the drought that began in around 2021, 2022 or so is the final yellow box on this plot. And just looking at it in that context, right now it looks like we're in the middle of the second worst drought on record. Even though rainfall has been close to normal, we haven't had those above normal periods that produce large runoff, produce large recharge to aquifers, produce large inflows to reservoirs. And that's basically the problem we're having. And yeah, if you look at the past 50 years, if you start in the middle of that very wet period, there's a massive downward trend. So of course, the million-dollar question is that trend going to continue? Is this something we expect to see persisting? And the answer, at least to me, is no, we don't expect such a dramatic trend to persist. We may have, in some sense, returned back to normal. Climate change, of course, can cause lots of different things to happen, but the projections for climate change as a function of the magnitude of change from a 1.5 degree global warming in the upper left to 4 degrees of global warming in the lower right, which is sort of a worst case scenario. You see, no matter how much the climate changes, the models have Texas sort of in between getting wetter and getting drier in terms of rainfall. And this plot obscures a fairly big spread between the model projections. There's a few models that say Texas is going to get a lot less rainfall. A few models say Texas is going to get more rainfall. So it's really an open issue as to what we'll see happening. Although, as you saw from the large variations historically, those natural variations are still going to be the dominant factor. No matter if rainfall goes up 5% or down 5%, we're still going to have extended periods with plenty of water and extended periods of drought. Okay, extreme rainfall is even more affected by the topography, I think. This is a plot of the 100-year rainfall amounts, the amount of rain you might expect to see once a century, in this case over a 6-hour period. So the that's a typical duration for producing flash flooding in the hill country. And you see there's a prominent blue stripe across basically the Balcones escarpment. That uplift that produces more rainfall also can be a focal point for more intense rainfall and then potentially flash flooding. The whole area is potentially subject to flash flooding, but the amounts typically are larger toward the south than to the north. Now, you may occasionally wonder about how we can get several 100-year events in a single year, and the reason is this applies to the odds at a given spot. And if one location gets a 100-year event, the location nearby probably doesn't. So the truly exceptional events only happen rarely in particular locations, and they're much above that 100-year total. In fact, the hill country has seen some of the most intense rainfall anywhere in the continental United States historically. Here's a few examples. Not quite the hill country, just east of Austin, with long-standing record for intense rainfall, 36 inches in 18 hours. That same rainfall event produced flooding in San Antonio and was responsible for the flood control system we now know as the Riverwalk. July 1932, the biggest flood in Hunt up until this year. Almost 20 inches in 6 hours, again, almost 3 feet of rain in 24 hours. Rainfall event north of D'Hanis in 1935 is still basically a world record for 21.8 inches in less than 3 hours of rain. And in perspective, that's basically almost double the amount of rainfall that produced the flooding along the South Fork of the Guadalupe River. And you can see other storm totals, 3 feet and 4 feet and so forth. So I've got 6 highlighted in recorded history. So basically, every couple decades or so, we actually ought to expect to see something this exceptional happening somewhere in the region. And that assumes that the odds of exceptional rainfall are not increasing. But unfortunately, they are. With a warmer climate, we've got more capacity for water in the atmosphere. Storm systems can also be affected in terms of their structure. And here's an analysis of the historical intense rainfall that we've done across the southern United States. And there's lots of variations depending upon the weather. For example, Southeast Texas has a bigger trend than other places because they got Hurricane Harvey recently, as well as a couple other flood events. But if you average things together, we basically see an increase in 100-year rainfall amounts of about 15% over the past few decades. And that trend seems like it's primarily climate change and therefore would be expected to continue. Now, another thing that affects drought is temperature, because rainfall amounts depend upon what's coming down, but the amount of water you've got to use also is affected by evaporation. And what we see in projections, of course, is an increase in temperature across the whole United States. And those same models simulating temperature going up and rainfall staying about constant predict soil moisture to be decreasing fairly dramatically and already in the process of dropping. So that means, to some extent, that we will be a bit droughtier, perhaps, even if rainfall stays the same. Certainly, it suggests that that droughts will develop impacts more quickly. We'll feel those water shortages more acutely because of the environmental demand for water. And the plot on the left here is a plot of projections across the whole state of Texas for different river basins. The black symbols are different river basins. The colored symbols are different models averaged across Texas. And the point here, looking at the x-axis from left to right, soil moisture is projected to decrease in every river basin by every single climate model. Runoff is generally projected to decrease by a bit. We're looking at mean runoff. But interestingly and unfortunately, if we compare the projection for mean runoff down in the bottom here to the projections for the highest runoff totals, the amount that might occur once every 5 years or so, we see the average runoff expected to decline, but those flood events are expected to maybe stay about the same. So the lack of runoff persists over most years because soils are dry, those absorb a lot of the rainfall. But we occasionally get those very heavy rainfall events where the amount of water in the soil doesn't even matter because it's all basically going to run off anyway. And unfortunately, that means we still have to deal with floods, even though there's less water in the rivers on average. So that's like the worst possible outcome as far as I'm concerned, because it makes dealing with the water a challenge. Last hazard I want to mention is wildfire. Across the state of Texas, this black line here is showing the typical amount of acres burned month by month. The first peak is in March and April. The second peak is in July and August. So Texas has 2 wildfire seasons. Now, essentially, the peak on the right is the East Texas wildfire season. Summertime temperatures get high. You've got lots of pine forests. It's easy to get lots of small fires. But the peak on the left is the spring peak. And the red is what happens in basically the worst year of the decade on average. Each one of the individual lines are individual years. So actually, most years, we don't get a dramatic wildfire season in the spring, but every once in a while we do. If the weather conditions just happen to line up perfectly, essentially. You need 3 things to get a really bad wildfire season. One is lots of rain. Doesn't seem like that should be one of the conditions, but lots of rain the previous year to build up lots of grass growth and so forth. Then cold weather to turn things into dormancy, make things dry out, and then hot and dry weather coming associated with springtime severe weather conditions. And every once in a while that can be far enough south and east to affect parts of the hill country as well. The risk is higher toward the northwest in general, but as we saw in 2011, you can get hot, dry weather even in the fall, and the Bastrop Fire demonstrated that. We've been fairly lucky in the hill country avoiding those sorts of risks so far, but that risk is underlying, it's always present. So despite all this, the hill country is still habitable. I painted a very dismal picture of the climate, but it's actually a great place to live. It's a great climate. It's moderate in temperatures, but you have to respect those extremes of the weather that can happen. And especially keep in mind, just because it hasn't happened yet doesn't mean that it's possible. So it requires caution, it requires care, but it makes the hill country what it is. So thank you for your attention.
Thank you so much for ending on that note of optimism. I was starting to lose hope for a minute there. I'm going to see if I can ask Ben and Roel, as 2 of the Hill Country Alliance's board members, would you all mind standing up and grabbing some microphones we have a few minutes. Thank you. My next Vanna White, Roel, Ben Eldridge. So let's take a few questions from the audience. Raise your hand.
I don't need a microphone.
Well, let's make it for our folks online.
Okay.
Good morning. So while these floods kind of seem out in the middle of nowhere, how much is development pertaining to these events? And making things flash floods so nothing soaks in.
Yep, so there's not a lot of urbanization in the hill country. The main impact of development is creating impervious soil conditions where water can run off quickly. And the hill country is not very vulnerable to that because its soil conditions allow water to run off fairly quickly anyway. So development in the watershed doesn't matter much. Now, what does matter for people in harm's way and so forth is development along the river, which can affect the size of the floodplain, as well as, of course, put people in a position where they're vulnerable to being affected by the flood. So that sort of thing is the main issue regarding flooding and development.
Other questions?
My name is Dick McBride, Hayes County Master Naturalist. In the past, they've had come up with all these plans to divert water from the east to the west. And a lot of times it's the Mississippi River. Well, you know what? We can do it all in Texas. You got Houston down there with tons of water. We have incredible amounts of cheap energy available if we do it with solar and wind. So we could pump that stuff west, maybe even start putting some of it in the Ogallala. But anyway, I think, you know, technologically, it may be feasible. California built the big system they have out there. But anyway, rather than have to go and talk to other states, maybe we can do it all in state or at least help a lot.
Yeah, thanks for that question. It is technologically feasible. The challenge is making it politically feasible. In particular, making it worthwhile for East Texas to give up its water and its potential capacity for development to support other parts of the state. So that's where the challenge lies.
Well, we have time for one more. Oh, great.
Wow, that soil moisture graph is going to haunt me. Can you speak to the relationship between soil moisture and possibly like clear cutting or overgrazing, maybe plant life?
Sure. So soil moisture is affected by vegetation, but there's two factors that are affected. First off, more vegetation leads to more transpiration. The plants are using water, so greater amounts of plants, greater amounts of shrubs, greater amounts of junipers, they suck more water from the soils. But it's primarily from the deeper soils that they're drawing the water from through the root system. If you have more bare ground, then you've got less total evaporation, but the water is being drawn directly from the soil itself, which is being hit by sunlight. So the top part of the soil gets very dry, but you actually preserve more water underneath. So it's a fairly complicated interaction there.
Well, please join me in thanking John Nielsen Gammon.
Thank you.